Right, when I saw you last, we were speaking about the electroscope. Right, can anyone tell me what is the purpose, what's the function, what's the job of an electroscope? Purely that. Does it tell you what charge? Yes? No? Does the leaf go up with positive, down with negative? Yes? No? What? So it would separate. And if it was negatively charged? So the leaf will also separate from the rod. So it doesn't tell you what charge you're talking about. Okay. Let's just have a look at what an electroscope looks like. We're not going to draw it absolutely accurately. Right, there's your metal rod. There's the gold leaf attached to the rod. And what did we say you had around it? What's that? Yes. Metal. Okay, as long as they can conduct electricity well, that's all you want. Everything else can be made out of plastic. So you want your metal disc, your metal rod to be made out of steel, conducts electricity well, and your gold leaf must be a lightweight metal, and gold, because you can roll it so thin, becomes a very lightweight metal. Okay. A metal could be a T-bar. It's normally a flat area where you can put a charge on. Okay? So it would be something like the top of this jar. So say if this ruler was charged, I'd do that and rub the charge from the ruler onto the disc. If it was just a narrow strip thing, it would be a bit difficult to get the charge to transfer onto it. Okay, you've all got that. Now, if we just talk about it, this is just a metal disc. It's normally about that size. A metal rod, gold leaf. That is the important part of the electroscope. The only reason it's got this case around it is so that the gold leaf doesn't get blown around. Otherwise it would blow and break off. So the case is meant to protect it and prevent breezes from making it look as if the leaf is lifting when it's not lifting. To be able to see what's happening, you've got a glass window, usually on both sides, the front and the back. And what's this washer or this insulator there for? So that any charge that you put onto this blue disc and rod, does that charge get into this box? No. So it's like a rubber or a plastic insulator that prevents electricity from running off. Okay? Right. So that's what it is. It's simple. What normally happens is you'll come along with something which is charged. How would I charge this ruler? Rub it through your hair. Okay. Hair dryer, under your arm, on your jersey. Anything like that normally generates charge. Okay? So let's say I've managed to put a negative charge on this ruler. What does that mean if this ruler is negatively charged? Can anyone tell me what it means? It's got too many electrons. It's got more electrons than protons. If it was neutral, if I neutralized it by touching it, okay, your body is a big dam for electrons. Your body can absorb extra electrons. So if something's got too many electrons, you touch it, those electrons flow from the ruler into my body, and this thing becomes neutralized. If this thing is positively charged, how do I neutralize it? Touch it, what happens? The electrons flow from my body into the ruler and neutralize the extra positives. Okay, so if something is neutral, tell me about the protons and the electrons. They equal in number. 20 billion trillion electrons, 20 billion trillion protons. Equal number. What's the overall charge? Neutral. If this thing is negatively charged, what is the case? It's got more electrons than protons. So it's got too many electrons. Okay. So what are these electrons doing to each other? They try to get as far away from each other as possible. They repel each other. I touch the ruler onto the disk. What are these electrons now? What do they suddenly see? Here's an extra space to spread out. So the electrons jump onto the disk. Where else can they go? Down the rod, where else can they go? Onto the leaf. Can they go onto the case? No. Okay. So have all my extra electrons left the ruler and jumped onto the electroscope? Yes or no? Have all the extra electrons that were on here, the excess electrons, have they all jumped onto here? Serious, why would they all jump on? This can become neutral, then this has become charged. Surely they will distribute themselves. The extra electrons here will distribute themselves so that I've got a few extra electrons here and a few extra electrons here. That gives them the biggest possible area, the least repulsion. All agree? So so this thing will never become perfectly neutral by touching it on there. Okay? What will happen, it will lose some of its negativity, and this will become slightly negative. They'll share that extra negative charge. By? How do you mean I'm measuring it? If any instrument that measures anything changes it. If your speedometer on your bike measures the speed of your bike, it actually slows your bike down. Because your wheel is going to turn a cable which turns the speedometer needle, and that slows the wheel down. Anything which measures anything slows down whatever you're measuring or reduces what you're measuring. Okay, so if this thing had a little dial here which said 20 coulombs, 10 coulombs, 5 coulombs, 0 coulombs, in touching it you'd actually reduce the number of coulombs on here. But either way, so we touch it, so what happens to this thing? It becomes less negative. This becomes more negative, and what happens to the leaf? Why does it repel? Why does it lift up? Okay, so let's just make a note here. Charging an electroscope negatively. All right, now I'm not going to draw the whole electroscope box and everything. What's the only important part in that electroscope? The T and the leaf. Okay. There's the T. There's the leaf. And here's my object like a ruler that I bring closely, and this thing is negatively charged. It's got extra electrons. Luther, I had to speak to you the other day about talking during lessons. All right. Can anyone tell me what happens in the next sketch? I touch it on. Where do those electrons go? Some of those electrons, so now it's actually touching, will move on to here. Do you agree? Some will move on to here. And some will move on to the, and some will still be remaining on there. And the leaf will now repel. Maybe I can show a few more electrons there. All agree? And in the last sketch, I can take the ruler away. And I will show that the electroscope has been negatively charged. In which direction did the electrons flow? In which direction did electrons flow over here? From the ruler onto, and I'm going to show a little E negative next to it to show that that's the direction that the electrons moved, okay? From the ruler onto the electroscope. You've got to go soon? 5-2. Okay, right, what do we do if I'm charging an electroscope positively, or are you still busy taking down the other one? Okay, let's just listen for the next one. I'll give you time to write down just now, so pay attention. I've shown in this one that I've used what type of object to charge it? A ruler. Over here I've deliberately drawn it differently, just to show that a ruler, the same ruler can't be used to charge something negatively as you're going to charge something positively. So what must the charge on this object be? Let's say it's a piece of glass. What must its charge be? Positive. Okay. Now glass becomes positive when you rub it with silk. You don't have to know all these things, what makes things positive and what makes things negative, but you'll take a positively charged object there. Right, when it touches, what's going to happen? So you say electrons from the electroscope are going to move onto the rod, or will the positives move onto the electroscope? You may go. Can positives move, Jonathan? No idea. Where do you find the positives, Puleng? Don't shake your head. We had it all written down this morning. On which particles do you find positive charge? On which particles do you find negative charge? Electrons. On which particles do you find positive charge? Where do you find the protons? Do you go and buy a box of protons somewhere? Where do you find protons? Where have you heard the word protons mentioned? Armella, can you tell me where you've heard the word protons? About? Any? The nucleus. So you're saying you find protons in the nucleus of an atom? Yes. And the nucleus of an atom is extremely tightly packed. I did tell you earlier this year that if you had to take the planet Earth and squash it down to the size of what? A soccer ball. Remember? You take the entire planet Earth and crush it down so that it is now the size of a soccer ball. Imagine how tightly packed it would be. That's how tightly packed a nucleus is. So do you think the protons are going to be able to get out of the nucleus and leave? Protons, positives, stay. They cannot move. Electrons are in the electron cloud. They're buzzing around. They can move. So yes, therefore electrons can move. But the protons can't move on. But what can happen? What can happen? Electrons can move from here onto there. Okay? So you can get electrons moving that way. And now what happens to all these positives? Every time an electron teams up, what happens to a positive? It becomes neutralized. So I can take out some of those positives, can't I? So instead of having maybe 20 positives, I'm going to end up with a lot fewer. Do you agree? So let's say I've only got 5 positives left. How many electrons did I take off here? There were 20. I've only got 5. How many electrons did I take off? 15. So how many positives must I draw here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There we are. You all agree? And now, when I take the glass rod away, you don't have to go and count positives. Just understand what happens. So we can write in both cases note. What do I want you to note? Only only electrons move. Right, that's all I've got to say for today. We'll wrap up the lesson at that point.